Welcome back, everybody. So we're in section 2.4, and we're covering the chain rule. And this is probably the most important rule for derivatives, because every time we take a derivative, we're applying the chain rule. We just don't realize it. So it's kind of this really powerful rule for compositions, but it's represented in every function that we work with. So let's go ahead and take a look at its description. So we've got a composition of two functions. We should note f and g are both differentiable. So f and g are both nice differentiable functions. And y equals f of g of x then is also differentiable. So differentiability passes through with composition as well. So we're going to have everything nice and differentiable. So what we end up with then when we take the derivative of f of g of x is we get this expression here. So f prime of g of x and g prime of x. So each function is going to be playing a role in the slope value. The first is going to be the derivative of the composition itself. The second is going to be the derivative of the function that we are putting inside of f, so that g of x function. So again, f prime g times g prime. F prime g times g prime, and this is going to get a little bit more complicated too, because we can have something that has multiple compositions. So if I had something with multiple compositions, you might wonder, well, what is that derivative going to look like? So the general rule is that we're taking the derivative of the outside function, so this is our outside function f, times the derivative of our inside function g. So outside versus inside. But now I've got h inside, g inside, and then f is outside. So there's like one inside function with an outside function with another outside function, right? So it's going to get a little bit more complicated for sure. But if I were to take the derivative of this using the same idea, it would be the derivative of the outside. So that's going to be f prime of g of h times the derivative of, let's say, the first inside function. So that would be g prime of h of x times the derivative of that further inside function times h prime of x. So f prime of g of h times g prime of h times h prime. And if we added a third composition, we would do the same thing where we're just layering each one of those derivatives in. Now the proof of this is going to be a little bit beyond the scope of our class. Your textbook has a nice proof of it that's a little bit simpler than most proofs. So most proofs are a little bit more careful, but it is definitely worth looking at that if you're interested in the proof, but we won't be covering the proof here. So another way of writing it is using what we call kind of a substitution. So we make some sort of substitution that represents that inside function g, and then we do this kind of layered multiplication. So dy dx is the same as dy over du times du over dx. And we can see that this is going to be true because du is going to cancel here. And so what we can do is we can add these substitutions to separate each part of our derivative. And then that separation will make it easier maybe to see. So I'm going to kind of present two different ways of approaching it. One is going to be that f of g representation, and the other one is going to be the dy dx, or y equals f of x representation. So in the note just below there, so again, I kind of have an explanation down here that might be worth reading. So derivative of the outside times derivative of the inside. But also it helps to identify those compositions, and there can be more than one. So let's keep that in mind. So if I look here, right, we've got f of x equals the square root of 2x cubed plus 4x. I would probably recommend rewriting this as 2x cubed plus 4x to the 1/2 power. But again, you can use square roots if you want to. And so I think clearly we can see that our inside function g is going to be that cubic polynomial. And then our outside function f, or if you want to call it h or some other letter, let's just call it f for the moment since it's f of x over here. Then f, the outside function, is just that square root function. Okay, so let's go ahead and compute the derivative here. So the outside function is our square root, so the derivative is going to be the derivative of a square root. Now to start that might seem a little kind of wonky. Like, how am I going to do this each time? So what I'm going to start with then is using the substitution method. So I'm going to use the substitution method that we discussed. So we'll note that, that this is y, so y equals the square root of u, or f equals the square root of u. So our substitution then is going to be of that inside function. Okay, so u equals 2x cubed plus 4x. And then I could go further if I needed to, but actually 2x cubed plus 4x is pretty easy to differentiate by itself. So what I'm going to do below that then is I'm going to take each one of these expressions and I'm going to differentiate them with respect to x. And then this one I'm going to differentiate with respect to u. So again, I'm choosing d du here because my variable that I've substituted is u. So that's my independent variable that I've chosen. And then here I've got u as a function of x. So x is my independent variable. So when I take the derivative of both sides, for y I'm going to get dy du. And then the derivative of the square root is just 1/2 u to the negative 1/2. And then the derivative of u is going to be du over dx, which is 6x squared plus 4, using the power rule. And then I'm just going to combine those. So dy du is equal to, dy dx, so my true derivative is equal to dy du times du dx, which is going to be 1/2 u to the negative 1/2 times 6x squared plus 4. But now I've got two variables and we want only one variable, so I'm going to substitute u to the 1/2 for what my original u was, which was that cubic polynomial. So what we're going to end up with is 1/2 times 2x cubed plus 4x to the negative 1/2 times 6x squared plus 4. And that's going to be our answer. So again, where I started here was defining what my substitutable value would be, which is that inside function. And my inside function was that cubic polynomial. And so I took y and u separated, where I had y was equal to the square root of my composition, and then u was equal to the inside function of that composition. Differentiate them separately, and then combine them as a product. Okay. So let's look at a second example here. Okay. So we've got g of x equals 9x cubed plus 7x squared plus 1 quantity to the 4th. So what I'm going to do here is use this kind of shorthand method for this. So I can see that the inside function is the cubic, the outside function is the 4th degree power term. So the typical way you're going to approach this by differentiating is differentiate the outside, which is the 4th degree expression, times the derivative of the inside, which is that cubic. So the way this is going to look is 4 times 9x cubed plus 7x squared plus 1 to the 3rd. So that is the derivative of my outside function, which was that power 4 expression, times, now I'm going to differentiate the inside of that cubic, which is going to be 27x squared plus 14x, and then the 1 is just going to become 0. So when we apply the chain rule in this f of x way, we can do it without this, long substitution process. So eventually we'll probably end up here, but let's go ahead and verify this using that u substitution method that I discussed in the first example. So we'll note that y is equal to u to the fourth would be our substitution. So y is equal to something to the fourth power, where our something is this cubic polynomial. And then we can differentiate with respect to u. So we'll get 4u cubed, and then differentiate with respect to x. And we'll get 27x squared plus 14x. Then we'll combine those. So we'll have dy dx equals dy du times du dx, which is going to give us 4u cubed times 27x squared plus 14x, which again, when I substitute that in, I'll end up with what I started with up at the top there. So that second method of just kind of visually looking at what your outside and inside are and taking all of their products with their derivatives is going to be faster. So this method is going to be faster, but you have to be really careful and make sure that you see what are your inside versus outside components of your composition. Okay, so just be careful of that. So that's going to be our chain rule. And so we've got a couple more. So we've got 3, 4, 5, and then 5, number 2. So I always like to include some misnumbering. So let's go ahead and kind of work through these. So for number 3, we've got cosine cube theta. What I'm going to recommend for trig functions is to always, always, always rewrite them so that you can identify the composition. So cosine cube theta is the same as cosine theta quantity cubed, because now I can see my inside function, which is cosine, and my outside function, which is the cubic function. So again, you could use a u sub if you want to, but I will use that kind of more direct method. So h prime is going to be the derivative of my outside function, which is that cubic. So I'm just going to use the power rule for that cubic expression, times the derivative of my inside, which is cosine. So that's going to be negative sine theta, and then we can just distribute the negative sign, and we'll get cosine squared theta sine theta. Again, though, if you want to, you could do y is equal to u cubed, and u is equal to cosine theta, and then work it out from there using substitutions. And just note, this is f prime of g, and that is g prime. So f prime of g times g prime. Okay. For number 4, we've got k of t equals 2 over 1 plus 2t to the fourth. And I'm going to give you kind of another helpful hint here that is going to be very useful. So if I'm looking at number 4, I might say, oh, I need to use the quotient rule. However, if I look at my numerator is a constant. So if my numerator is a constant, what might be more useful to do is to rewrite this as 2 times 1 plus 2t. Now bringing the expression to the numerator means I have to change the sign of the exponent. So that would become 1 plus 2t to the negative 4. And then now I can just apply the power rule when I'm taking my derivative. I know the 2 doesn't matter, so it's just a coefficient, so I can leave that on the outside. So if I'm taking k prime of t, that's going to be 2 times, and then now I can apply my chain rule to the expression that I have. So my inside function is 1 plus 2t. My outside function is something to the negative 4th, so the negative 4th power expression here. So what we're going to end up with is the derivative of something to the 4th is going to be negative 4, 1 plus 2t to the negative 5th, using the power rule, times the derivative of the inside, which is just 1 plus 2t, so the derivative of that is just 2. So again, this is going to be f prime of g and g prime. And so we can clean that up by multiplying everything through, and we'll get negative 16, 2 times 2 times negative 4, and then 1 plus 2t to the negative 5. We could leave that as is, or you could rewrite it. Totally up to you. So again, both forms would be equivalent. Doesn't matter which one you use. But the key here is avoid using the quotient rule, because the quotient rule is just going to add more time that it takes to compute. So this technique of changing that to a negative exponent expression in the numerator is a very useful tool. And again, that's our derivative. All right, so let's take a look here. Okay, now we've got cosine cubed 8t. All right, so let's take a look at this first. We should rewrite this as cosine of 8t quantity cubed. Again, rewrite it as quantity cubed so we can identify all of the compositions here. And now we have an example with two compositions. So inside of my cosine is 8t. Then I have cosine of that 8t. And then I have the cubic expression. So I will write this kind of in that quick method first, and then we'll look at how we would do this with substitutions. So let's go ahead and compute this. Let's see, do I have enough space? Yeah, I think so. All right, so let's go ahead and try over here. So y prime. So if I'm taking the derivative, again, starting outside and then working in, so the derivative of the outside is going to be 3 cosine 8t squared, right, my cubic, times the derivative, now the inside is cosine. So I'll take the derivative of cosine, times what's inside the cosine, which is 8t. So it's going to be times 8. So note, this is going to be h. This is going to be g of h, or g prime of h, sorry. This is h prime. And then this is going to be f prime of g of h. So this is that kind of nested composition of functions. So that's what our answer would be. Now let's go back here and let's look at what we could do if we were going to do substitutions. So if we were going to do substitutions, we'd start with y equals u cubed. U equals cosine of v, and then v is equal to 8t. So we kind of keep adding variables until we get to our original independent variable. Then we can do dy du, which is 3u squared, du now dv, since I've named this new variable v, which is negative sine v, and then dv dt, which is just going to be 8. So the derivative with respect to t of v. Okay. Then we'll just mash these all together. So dy dt is going to be dy du times du dv times dv dt. Again, we'll get that cancellation all the way across till we get dy dt. And so we'll get 3u squared times negative sine v times 8, which when we resubstitute then is going to be 3 cosine 8t squared times negative sine 8t times 8. All right, so we still get the same answer that we got before with kind of that shorthand method, and then we would just need to multiply to make this negative 24. 8 times 3 times negative 1, and then we'll have cosine squared 8t sine 8t. So that's going to be our final answer. So as you add more compositions, you're going to add more letters. U, V, W. You could do A, you could do B, you could do other letters if you want as well. U and V are just kind of the standard letters used. All right. Let's look at the last one. So we've got tangent of cosecant of 2x. Again, another nested composition. So we've got 2x cosecant 2x, and tangent. So we've got three separate functions. You could do the u substitution and the v substitution. I'm going to do kind of just the shorthand. So we'll start with the outside, which is tangent. So the derivative of tangent is secant squared. Okay, so again, it's just secant squared of whatever's inside. So that's my outside function in red, times the derivative of cosecant 2x. So the derivative of cosecant is going to be negative cosecant cotangent. And then the derivative of 2x is just 2. Right, so we get this kind of complicated looking expression. We can clean it up a bit by putting the negative 2 in the front. And then we'll have secant squared cosecant 2x times cosecant 2x times cotan 2x. And note, be very careful here. Cosecant 2x is inside of the secant. So cosecant 2x is an angle measure in that secant squared expression. So we cannot combine those. And that's it. And so again, if you do the double substitution, you'll end up with the same answer. All right. So on the next page, we've got a couple more examples. So I think I'll stop here, give ourselves a little breather here. And again, if we have questions on any of these, feel free to email me or come by the office hours.